Um, just having some electrical issues here at APK. Just having some power issues at APK, but my connection is back on. So good morning to all the participants and good morning to you again, Ms. Smith. Thank you so much for joining the session, to all the participants, and thank you so much, Ms. Smith, for preparing to facilitate this session. My name is Lawrence, and I am delighted to be your facilitator, and I'd like to thank all the participants for taking the time to join, and most importantly, our presenter for taking the time to prepare this presentation. Before we begin, I'd like to just go over a few housekeeping rules, as I think most of you are aware of. If you do have any questions during the sessions, please kindly raise your virtual hand, and I will indicate to the presenter to address your question. Or also, if you do not wish to speak, please type in the chat box and I will address your question as well. And as I have indicated, that this session is being recorded and the presentation slides together with the recording of this workshop will be posted on our model communities. I'll also be posting a feedback survey in the chat session to kindly rate this session, and we also use this feedback for our reporting purposes. So as Ms. Smith mentioned when we started this series of workshops, that in the feedback survey, please highlight things that you think maybe she might have missed, or things that maybe you think will be relevant to your research and all that. So please just indicate also in the chat or indicate also in the feedback survey when you're filling it in, so that she knows which areas can be improved and which areas we can go about further coming. So in that regard, would you please allow me to read over Ms. Smith's bio. Ms. Elsabo Smith started her career as a statistician at the Rand Afrikaans University in 1994, completing a BS Science and Mathematics. While studying at Ms. Elsabo worked at the Statistical Consultation Services, first as a student assistant and later as a data analyst. After graduating, Elsabo moved to Cape Town and worked as a statistician in market research for 5 years. During this time, she completed her honors in mathematical statistics at Stellenbosch. Ms. Elsabo then enrolled at UNISA for a postgraduate certificate in education. She worked as an educator in England for a period and spent some time traveling through Europe. Upon her return to South Africa, Ms. Elsabo joined another market research company as a senior statistician for 3 years while studying for an MS Science in mathematical statistics at Wits. From 2009 to 2016, Ms. Elsabo worked as a senior tutor in the statistical department at the Wits University, where she taught statistics services courses to students in commerce and humanities. Since 2017, Ms. Elsabo has been a lecturer at the statistics department at the University of Johannesburg, where her statistics journey began. So in that regard, I'd like to hand over to you, Ms. Smith. Thank you so much.
Thank you very much, Lawrence, and welcome to everybody that joined the session. I'm going to share my computer, my screen. For the session, what I've done is I've prepared a few documents. It's not a presentation slide, but because we're going to be working in Excel. But I've also got this document that I've put together many, many years ago, and thankfully I found it, and maybe it will be useful. I'm happy to share it with everybody. So let me just zoom in a little bit. When you do research, when you do your analysis, you set up your problem statements and you have things to investigate. And it's important that you use the appropriate tool to address that. So this flow chart highlights most of the statistical, many of the statistical techniques that could be used. You're not going to use all of this. Make sure that when you do research, you use the appropriate technique to address your problem statement. It doesn't make sense if you're proposing everything that's in the toolbox. It is important to use the right technique. So this structure is where I've grouped things in two main categories. The one set is the interdependence techniques. With that, I mean there is no dependent variable of interest that we are trying to predict or model against. And then we do have the dependence techniques where we have a dependence variable, such as regression analysis. For the interdependent techniques, if you've got bivariate, only two variables at a time, or multivariate, multiple variables, that takes us into whether I've got categorical or numerical data and the kinds of techniques we can do, such as the chi-square test of independence, Pearson's correlation, etc. From a multivariate side, depending on the nature of the variables, we can do data reduction techniques such as factor analysis, cluster analysis by identifying subgroups, techniques like canonical correlation and multidimensional scaling. I'm not sure if that's the kind of techniques that you'll be using. They're not often used. PCA or factor analysis and cluster analysis is quite common. In terms of the dependence techniques, we have where we're dealing with group differences, that's on the next page, and then the relationships. And it all depends on how many dependent and independent variables we have. So the DV stands for dependent variable and IV for the independent variable. So if I've got one dependent variable, one or more independent variables, then I can do regression analysis, or I can do discriminant, logistic regression, chain analysis, which is a decision tree structure, etc. If I've got multiple dependent variables, we go into the multivariate type analysis like MANOVA, conjoint analysis, or structural equation modeling. And then on the next page, I've got the grouping. If there's all group differences, if I've got paired observations or independent groups, depending on whether I've got two groups or more than two groups, we do things like the paired samples t-test, or the repeated measures ANOVA, but I'm also listing whether it's parametric or non-parametric. If I've got independent groups and I've only got one independent variable for a single group, two groups, or three or more groups, for those of you who were in the session for yesterday, I spoke about things like the one sample t-test, the independent sample t-test, and the one-way ANOVA, and I'm also listing the non-parametric equivalent of that. If I've got multiple independent variables, we go into what we call factorial ANOVAs, like a two-way or a three-way ANOVA. So I'm very happy to share this flowchart with you if you think it may be useful. And on that note, let me turn to what I'm going to do today. So I've got a Word document here, which I will save as a PDF with a few data sets and some information about data sets. I've got two data sets and then another data file in Excel with some contingency tables that we are going to use to create chi-square tests. So the movie data is the first one we're going to look at. So I give some background and then a few questions that we can deal with. So in Excel, excuse me. So the movie data, it's an investigation done to determine best predictors of gross revenue of movies in the United States. Now I've got a whole list of movies from 2010 to 2012. We have the gross revenue, the budget, the runtime, and the critic score. So the gross revenue and budget are all in millions of dollars. And also tell you how the critic score was created. So this is what the data would look like in Excel. If you want to do statistical analysis in Excel, you have to have the data analysis tool pack installed. So it falls under the data tab. And right here on the right-hand side, it's something called data analysis. If you haven't got that, you must activate it by going to File, right at the bottom to the Options. It brings up this tab, and there's a whole load of things over here. Under the Advanced, add-ins. You have to go to Add-ins. And under Add-ins, what you look for is the Analysis Tool Pack. And mine is already installed, but you will click on it, and you'll say OK, and it will install this tool pack. If you're still not sure, just Google is your friend. Type it in, and Google will also give you the instructions on how to install that. So then you have under the data tab, the data analysis tool pack. Let me click on that quickly. And there are a few things that you can do. ANOVA, correlation, descriptive statistics, the F-test for variances. What else is there? There's histogram that you might be interested in, regression, t-tests, and so on. So those are the techniques that are built in. Now for for my data, before I work with my data and start doing statistical analysis, I need to get a sense of it. And we just make sure our data are in the right format, number one, and number two, that there are no errors in the data. And the typical structure of a data file is where I have my variables in the columns. So in this data set, I have got 6 variables, and then I've got my observations or my sampling units in the rows. So for this particular data set, I have got 362 rows, but that includes my names of the variables at the top. So I've got 361 rows of data. So that's the structure of my data file. Excel is not the best statistical analysis tool, but if that's the only one you have, you can still do some things. So we can actually just select the top row, and under the Home tab, under Editing, we can insert a filter. And in this filter, this allows me, excuse me, to very quickly have a look at the list. If I look at this particular variable, the entire list comes up, and the lowest number is 3.76, and it goes all the way up to 623.36. So it gives me kind of an idea of what is in my data, just a brief overview. And let's say one of these numbers was negative, and it didn't make sense, or there are blank spaces. That I can pick it up here very quickly and very easily. The budget, again, it goes from the number 1 up to the number 250, and I will quickly squiz through that to see if it all makes sense, if it's reasonable. If I have a number that, say, the value is minus 100, now that doesn't make sense to say my budget is minus $100 million. That would be an error. So this is a quick way for us to just look at our data. Right, and then I can take the filter off if we want. Let's have a look at the analysis that we're supposed to do. First of all, when we do analysis, the first thing we're going to do is to do descriptive statistics, frequency tables, and some graphical representation of my data. So my first question here that we need to address is create summary statistics for all 4 numerical variables, things like the mean, the mode, the median. Now, the power of Excel is that we have a lot of built-in functions that we can use to find individual values. But as part of the analysis tool pack, there is something called descriptive statistics. So if I go to Data, click on Data Analysis, and close to the top, there's the descriptive statistics option. Click OK. And I now have to select my variables. It has selected, or I can just go and select my columns from C to F, because I don't want to do descriptive statistics on the year or the movie. For this, it doesn't make sense. I've got 4 numerical variables. My variables are grouped by columns, the way it's supposed to for the structure of data and statistical analysis. I've also ticked this labels are in the first row because I've included that in the 4 columns. And we can put the output either inside the sheet or in a brand new worksheet, which we can call summary stats or whatever you want to call it. So it's a new worksheet. I click OK, and it creates in a moment. There we go. My summary statistics. It always puts this new worksheet before the one that I've been working with, the movie data. And it gives me, for each one of those 4 variables, a whole list of, I'll enlarge this a bit so you can see better. Mean, the standard error. Remember, the standard error is just the standard deviation of the sampling distribution. Typically, you won't report that at this point as part of the descriptive statistics. You'll do the mean, the median, mode, standard deviation, variance, kurtosis, and skewness. So the skewness coefficient just tells me, do I have skewed data or approximately symmetrical data? And if I've skewed data, is it positively skewed or negatively skewed? So you can always just do a Google search to say, how do I interpret a skewness coefficient? And it will say things like a number greater than 2 implies extreme positive skewness and so on. Kurtosis as a measure of the peakedness of my distribution. In other words, is it very peaked or is it quite flat? I always use the example, flat like Table Mountain or very peaked like Devil's Peak in Cape Town. It also gives me the range of the values, the minimum to the maximum. It adds a lot of information that you may not need, like the sum or the count. At this point, we don't need that. But I can look at this and say, all right, so this data, this variable itself ranges from 3.7 something to 623 and some decimals. It also helps me to determine in a very quick way whether it makes sense. All right, so that is my summary statistics. I'm just going to move the sheet to the other side. I like to have my data as the first sheet. And that is how we've dealt with our first question, getting descriptive statistics. Next question is to create a histogram of the budget variable. So to create a graph in Excel, under the Insert tab, all the charts are listed here under the Insert tab. So we've got bar graphs, stacked bar graphs, or the tree map, line graphs, the histogram and the box and whisker plot, then a few other combination plots. You can play around with it quite a bit. There's my pie charts, as well as the various scatter plots that we can do. So for this particular question, we said create a histogram of the budget variable. So I'm just going to highlight my budget variable, and I'm going to select the histogram. So the histogram, there we go. Click on it, and it automatically inserts a chart on top of my data here. And if you don't want it in this position, you want the chart in its own sheet, Excel sheet, I can right-click on the graph and say, let me just find it, move the chart to a new sheet, which I'm going to call histogram. And it will open up a new sheet, a new tab. I'm just going to put it at the end. And there is our histogram. So the built-in function for histograms in Excel, it uses an algorithm to determine the reasonable number of class intervals here and what the actual class intervals are. You can add a chart title. You can add whatever you like here. We can add a label for the x-axis, a label for the y-axis. So if you want to do additional things to the graph, we click on the graph, and then you'll see there are two things. The one is the chart design, and the other one is the format. So under chart design, you can change the look and feel of it. There are different built-in functions or built-in ways of doing this. You can see if I just hover over a different style, it changes the format a little bit. But what I want to show you here is that add the chart elements. If you click on chart elements, we've got quite a lot of things here. The axis, how to just change the axis, so we can format that, or the axis titles, that's what I want to do. So what I'm going to do with this, I'm going to add under the axis title, the primary horizontal. And if you see, I hope it's visible on your side, it immediately added an extra text box at the bottom of my graph called axis title. And while I'm here, might as well add the primary vertical. But at this point, it just shows axis title. I need to change that. It's very small, but if you click on it, excuse me, select everything. What did we do? This is the budget, class intervals. I will change the font in a minute. And the vertical axis are show the frequencies. So this font is really very small. So if I go back to my home tab, I can change my font and just increase the font of the entire graph to a different one. Now it actually looks a lot better. So there are many things that we can do here. We can even click on these bars and go to format and say, no, I don't want these to be filled in with blue. Let's do the shape fill, and let's be from UJ and make it orange, or whatever the case may be. So there's a lot of flexibility in Excel graphs, and it's worth playing around with a little bit just to see all the different things that you can do. We can also add the actual values on top of these bars. So if I click on the graph itself and right click, there's an option that says data labels. And then I can add my data labels and it puts it right on top. So it actually shows the individual frequency counts on top of it. Now, of course, the default font size here is very small, so we can change that again. So lots of flexibility in terms of graphical representation. So there we go. There we have our histogram. Our next one is to say, create a line graph of the averages of the 4 numerical variables. So if I go back to my Excel, or the movie data, I have the summary statistics with the 4 respective means. So if we've already run this, what we can do for this, we need to create an input sheet for a graph such as a line graph. Because a line graph on this data, let me just show you what something like this would look like. It's a bit messy. So if I highlight any one of these variables, go to the Insert tab, select a line graph, and you see it makes something in this particular data that doesn't really make sense. What we're looking for are the averages of these 4 variables and put them in a line graph. So the one way to do it is to just collect the data from the summary statistics, or we can create the averages using the built-in function. So I'm just going to copy the names of the variables. And then for each one of this, I'm going to use the Excel functions. I'm looking for the average. So to do an Excel function, you always say equals. And now I'm going to say the function is average. Now put a round bracket. And I say average of what? So an average of this is not going to work. Let me try again. Let me do it properly. So the average of this number, the very first one under the gross, US gross variable, right down to the bottom, scroll down, hold the shift key on your keyboard and click on the bottom one, and it lists the entire variable, all those numbers. And now I just need to close the bracket and I press enter, and it's 77.47, which of course is exactly what we had with our summary statistics. But this is just another way of doing it. Now in Excel, if I copy this value for the other 4, what it does automatically is this column finds the average of all the numbers in column C. And the way I've just copied it to the next column, it automatically shifts it to the next column, column D. So it finds the average of column D. This one finds the average of column E and the average of column F. If it doesn't do it properly, you must always check this, that it does it properly, and you can just shift it or change the column indexing in my function. So there we go. We've got the 4 numbers. I will highlight this, go to Insert, click on my line graph, and I just want a line graph. Let's do one with actual points in it. And there we go. We have our line graph. So now I can change my scales. It already uses the labels that I've included, and I see those are the average values for my different variables. Right. I'm just going to put this, click on the graph and move the chart to a new one, and this is my line graph. All right, at this point, I'm just going to save my data. It's always a good idea to save it. And we can now address our next question. We're looking for scatter plots. So scatter plots of gross revenue, and that must be on the y-axis, and each of the 3 independent variables, budget, runtime, and critic score. And given our timing, I'm just going to show you how to do one of them, and then it's quite easy for you to then do the others. So to create a scatter plot, I'm just going to highlight, let's start off with the gross revenue with the first one, which is budget. And I'm looking for a scatter plot. So the scatter plot, under these points over here, and I put the scatter plot in. But the problem with the way I've done this now is that the first column I selected is automatically plotted on the x-axis, and the second column is plotted on the, excuse me, on the y-axis. And that's not what I want. Now, unless you go and create a new sheet with those two columns, copy it into the new sheet, and swap these two variables, the order. If I now insert the scatter plot, it looks a little different from the one I had before. So that's one way of doing it. It might be better or easier for you. So you know that that is your X variable is budget, and the Y variable is the gross revenue. Alternatively, you can access the data in the graph itself by right-clicking on it, on the graph, click Select Data, and edit this, the input. So I edit this, and it shows me the name. I can give it a different name. It links it to that particular cell in Excel. My X values is now using column C. But if I change the column C to D, and then for the Y values, change column D to column C, click OK, and click OK again, then I get the exact same graph. So as you can see, there are different ways in which we can do this. Now, I've already done it in, I'm going to just delete this graph over here because it's on another sheet. And there we go. We have our scatter plot between the budget and the US gross revenue. And I can now add labels. I can change the font size. I can even, for this, say for the X-axis, for the Y-axis, I don't like it showing the 2 decimal points. So I can right-click on that axis, say Format Axis, and say the number, the minimum and maximum, right at the bottom. There's an option for number, and change it to a decimal of 0. And you can see how that changes the scales. All right, so that's just one of the graphs, and you can create the other. So this is my scatter plot, which I also want to just move to the end because then it's in the order in which we have done this. Okay. I hope I'm not going too fast. If I'm going too fast, by all means, please tell me. Okay, what's our next question? I want to create a correlation matrix of the 4 variables. So back to our data. So these 4 variables, I want to create a correlation, all the pairwise correlations between them. I can use a built-in function to do a correlation between one column or the other, or I can just go to my data tab, select data analysis, and then I have the option for correlation. That's one of the things or options in the analysis tool pack. Click OK. And because I've highlighted those 4 columns already, it automatically picks it up. And it's already grouped by columns. That's the default. Labels are in the first row. And I will create a new worksheet, which we will call the correlation. Click OK. And there we go. We have our correlation matrix. It gives quite a lot of decimal values. So I will just change these decimal values under the Home tab. You see under the number in this ribbon. You can just change the number of decimals that it doesn't look so crazy. So now we have a correlation matrix, and we can see that budget is the strongest correlation with the gross revenue compared to runtime and critic score. Now, one of the things I know I said yesterday when we looked at, was it yesterday? Yes, regression analysis, is sometimes you can have a weak relationship individually, but the combined effect in a multiple linear regression model, it changes. Or vice versa, you can have a strong effect here and a less strong effect when I combine it with a whole lot of other variables. But nevertheless, what we're going to do, we will look at this and say, okay, there's clearly a positive relationship between all my variables, the budget, runtime, and critic score, and the gross revenue, because that's in the next question, the model we're going to do. And then I also look at the other correlations. I'll talk about that in a minute. Let me quickly go back to our next question, because what we want to do is to fit a multiple linear regression model to predict gross revenue using the other three variables. We've seen that there is some other positive relationships, some strong, some not so strong, between the independent variables and our dependent variable. And one of the things that we need to also look at when we look at regression analysis are the correlations amongst my independent variables. If these correlations are too high or very high, we have something that we call multicollinearity. Multicollinearity has an impact on our regression line, not on how good the line is, but the interpretability of the line. Think of this. If, for example, budget and critic score, this is just an example, if this correlation was in fact something like 0.95, that is a very high correlation. Then you can ask yourself, well, why do I need both variables? If you know the one, you just about know the other. So in such cases, when we have multicollinearity, we do one of two things. We either remove one of the pairs of variables that are so highly correlated amongst the independent set, or we make use of other multivariate techniques, such as principal components analysis, to remove the interrelatedness of the independent variables so that we can have the unique effects of each one of those variables on our dependent variable. All right. But in this particular case, those correlations, those three are quite low. So we can just go ahead and do our regression analysis where we must predict the gross revenue using the budget and runtime and critic score. Again, we will use I'm going to highlight it, go to my data analysis, and scroll down, and you'll see regression analysis. We click OK. Now, the default order for me now, I've got my Y variable followed by my three independent variables. But if it wasn't listed like that, your input range you can select by clicking on this arrow in this text box. Click on it, and I just simply highlight the column that denotes my Y variable. And then to go back to that tab or that window, click on it again and select the input range. Click on my arrow. I select my three variables as my three independent variables. I return. I've got the labels at the top. I'm going to put it in a new worksheet called regression. And then you have something here at the bottom that talks about residuals, standardized residuals, residual plots, and line fit plots, as well as the normal probability plot. You can select all of that, but it's a bit messy. Excel, this part of the regression analysis in Excel is not as well structured as, for example, using R or SPSS to really investigate the assumptions. So I'm not going to fit that or select that. It is better you can do it because we need to have normal residuals. We need to have residuals that are randomly scattered around zero, and there's a whole lot of assumptions that we're going to check, part of diagnostics. But in regression analysis, other software techniques are actually better to do this. But nevertheless, we can still get to this point where we have our model. So I'm just going to select this, click OK. The lines and error. Oops, the input range. Okay, let's try this again. Cancel. So let's begin again. Did I miss something? There's nothing funny in my data. Let's go back. Data, analysis, regression. That is correct. Column C. That is correct. D. Labels and hold thumbs. Still not. For some reason it's not. It worked yesterday when I tested this. I will try again. My apologies. I'm just going to select the data itself. Maybe that works. Without the labels. Now there are no labels. Oh, there we go. So of course, now it doesn't show the labels of the variables. Maybe if you play around with it, maybe I made some mistake, but nevertheless, those are the 3 variables that I can just change. And this is the typical output that you're going to get from a regression in Excel. And it looks similar to what you've seen yesterday, where we have the summary output, just do fewer decimals. And if I look at my R squared, it's 0.528, so 0.53, so 53% of the variation in my dependent variable is accounted for by this model. Now, that's not a bad fit because there's probably a lot more, many other variables that will have an impact on the gross revenue. So this is not a bad fit. My ANOVA shows me that this is highly significant. So the number 5.8e to the minus 58. So that is a highly significant result. So that's 0.00000 and somewhere along line A58. In terms of my 3 variables, I'd like to get my names of the variables here. Copy those 3 into the output. Paste, transpose, there we go. What I'm interested in here would be the p-values. So those are my p-values. And we can see that budget and critic score are highly significant predictors of revenue. They've got p-values that are very, very, very small. And runtime has a p-value between 0.01 and 0.05. So it sits in that strong evidence range. So all 3 are significant predictors, but the strongest one, or the strongest one is budget. Then we have critic score, and then runtime still has an impact, but it's not as strong as the other, but it's still significant. Right. So we've got a fair model here, and we can use this model to predict. So now we want to predict the gross revenue for a movie with a budget of $40 million. It's 93 minutes long and gets a critic score of 57. So I want to go back to my data. Sorry, I want to just remove that. There's also an extra sheet that I want to just delete. And this is my regression results. I want to quickly move back to the data just to show you something. So the US gross and the budget, both variables are given in millions of dollars, but the numerical values are not. For example, 100 with a bunch of zeros to show millions. So the unit of measure here is millions of dollars. So when I look at a number here and I see 100, I will read it as 100 million, or the value 25 is 25 million, etc., etc. Which means if I want to predict for a value of a variable of 40 million, I'm not going to use the physical number 40 million with all the zeros. The unit of measure is in millions. Therefore, the number that I'm going to use is just the number 40. So when we want to predict this, we can use our equations. So a simple way. So in regression, let me get to my output. I'll make this a little bit bigger so you can see. So the budget, we want to predict we have a predicted value of 40, or for a budget value of 40. The runtime, if I remember, was 93 minutes, and the critic score was 57. Right. What we want to do, the model itself is the intercept plus the coefficient for budget multiplied by the value of budget plus runtime coefficient multiplied by the runtime value plus the critic score coefficient multiplied by the critic score value. So I can use the built-in functions. That's wonderful of Excel. I don't have to whip out my calculator for this. So we can simply use the equals in a cell and say, create the product between this value, comma, this value, equals this value multiplied, I didn't say product, multiply, the multiply in Excel is the asterisk, multiply that cell value with this cell value and enter. And if I copy this for the other two independent variables, you'll see it just transfers to the next row. It's going to multiply the runtime coefficient with the runtime value, and then the same for the critic score coefficient with the value. The intercept's not multiplied by anything. It just is what it is. So I just say equals my intercept value. And now I just add all of these together. Highlight all of this. Under the home tab, I can just do the sum. And there we go. That is our predicted revenue. If I have a budget of 40 million for a 93-minute long movie that gets a critic score of 57, that would be my predicted revenue for such a movie. Right. And that is how we do correlation and regression analysis in Excel. Okay, I hope that that's clear. Are there any questions maybe at this point? Are you happy with this? Does it make sense? Okay, so maybe no questions at this point. In that case,
there's no questions at all.
Okay.
There's no questions at all in the chat box, and there is no hand raised.
Okay.
So I think maybe the participants are following at this point. So I think we can continue. Yes. Wonderful. All right. Thank you.
All right. So then we can move on to the next one. So in this particular data, this is the Rosenberg self-esteem scale data. So let me just go to the data and show you what it looks like. So the Rosenberg self-esteem scale data. So this is a psychometric measure that asks a few questions on a rating scale, and then those questions are combined. Now, I've just decided how to combine this myself. I'm not using the existing algorithm, so there may be some other algorithms, but what I want to illustrate to you is what we can do in Excel with this data to create a measure, which is measured on an interval scale of these 10 questions. So we've collected the following information: the gender, codes 1 and 2, where 1 is male and 2 is female, the ages and completed years, and then we've got 10 questions that are all on a rating scale. It's only a 4-point rating scale. So let me go back to my Excel document. So the details are given here. The rating scale questions, some of the questions are positively phrased and some of the questions are negatively phrased. Now, when I have a mixture of questions that are positively phrased versus negatively phrased, if I want to combine them, I cannot just combine them together as they are. I have to reverse code them. Let me show you the questions itself. For example, if you read question number 1 here, it's all positive. I feel like I'm a person of worth. The next one, I've got good qualities. Question number 3, all in all, I'm inclined to feel that I'm a failure. So the response to question number 3 should be negatively phrased or negatively correlated with responses, for example, in question 2. Because if I think I've got a number of good qualities, I'm in agreement with that, I will not agree that I feel like I'm a failure. So I've listed the questions that are positively phrased versus negatively phrased. So there are different ways in dealing with this. Number 1, if you've got a new set of questions, you will run these questions through a technique such as factor analysis or principal component analysis that will pick up the nature of the relationship amongst these questions and show you perhaps how to reduce the 10 questions to fewer questions. On the other hand, if it is a standardized instrument already that was developed through those processes and all the reliability and everything is checked around it, what you would do is have an algorithm to say it is question 1 plus question 2 plus the reverse of question 3 or minus question 3 or however the algorithm is structured. The way that I'm going to show you how we're going to do this is that we're going to reverse code all those negatively phrased questions. So I've got quite a few questions here that we can do. And we're first of all going to start by constructing a categorical ordinal variable of my variable age using the following categories. And we'll use a very simple methodology in Excel to do this. It's very useful going forward. Then we're going to do a pivot table so we can make frequency tables. We're going to create some bar graphs. We're going to construct the RSE measure, a few more, well, another graph, which is the box and whisker plot. And then we're going to do 2 hypothesis tests. So it seems like quite a lot that we're going to do. Now, so let's start with our categorical variable. So let's go back to our data for RSE. So if I put my filter on again, and I look at the ages, it ranges from 18 to 68. So a quick squiz through here. There's nothing funny going on here. So no problem. So those are my ages. So what I want to do is to group each one of these ages into an age range. Now, of course, you can go individually or sort the data from lowest to highest and then just change your data. By the way, you never overwrite your original data. We never ever do that. There must always be a copy somewhere of your original data. Don't just go change things, because what if you make a mistake? You can't go back if you've overwritten it and saved it. So what I want to do is I want to create a new variable called age category, and I'm just going to put it right over here, call it age category. And instead of typing in, this is 30 to 39, this is 30 to 39, I'm going to use a function in Excel to do this. So I've already partly set it up. So what we have is this. I want 3 categories. The one is from 18 to 29. Let's make sure. Let's go back to what we're supposed to do. So it's under 30, which means it's from my lowest value up to 29 years. And the next one is from 30 to 39, and then from 40 or more. So we set it up, the points, with the lowest limit of each one of those 3 categories. And next to it, I put the label. This is what I want it to do. We're now going to use the VLOOKUP. And I don't know if any of you have ever worked with a VLOOKUP. The VLOOKUP says, that function says, go and find this value in a set, amongst a set of values, give me something back, either find the exact match or find something approximate. Right, so that's the structure of VLOOKUP. So in this cell, I'm going to start with an equal sign and type VLOOKUP, put a round bracket, and I say VLOOKUP, the value in column B, only that one, put a comma. I'm now going to go to my age category list, and I'm going to highlight the 6 cells, these 3. So the lower limits as well as the labels. Now, before I go away from here, what I want is to keep this fixed. Now in Excel, if you want to keep rows and columns fixed, you put $sign. So I need to put a $sign after the column notation for A, a $sign after the row, $sign after B, and a $sign after 4. There is a shortcut to do it on your keyboard, the top row, function F4. If you select function F4, see what happens. So I said dollars after, it's dollars before. So $A, $2, up to $B, $4. Now, why am I doing this? It's because I'm setting this up for the first cell for value in B2. I'm going to create a category for that. And then I'm just going to drag that down so it does it for all my categories. And if you do this without setting the fixed rows and columns, when you drag it down, it's going to also drag this automatically down, and you don't want it to go look for nothing. It has to still stick with this set. So I'm looking up a number for age in this set. After this, I put a comma, and I now have to say, well, which column, which answer must you return? This set consists of 2 columns. You look up in the first column and you give back to me the second column. Give me the answer in the second column. Put a comma, and I now select either true or false. So true is the approximate match. False is the exact match. So I'm going to select true, but because it's not the exact match, I'll talk about that in a moment. So if I select true and close the bracket, go back and look at what happened. That is in 31 is definitely in the category 30 to 39. Now, if I just double click on this square right at the bottom of this cell, it's going to do this function for every one of my observations. And it will pick up all the different categories. So it saves quite a lot of time, right? What this true means is that it's not an exact match, it's an approximate match, and that's how it works. If I had, for example, the numbers 18, 19, 20, and I have a whole list of this, and let's say this is under 20, this is under 20, 20 to 25. Just giving an example here. Greater than 25. And if I want to do the age, look up the exact values, go back to my age categories. Now I can link the exact age value with my list. In this case, what you will do under your VLOOKUP is not to say true, but to say false. That means go find the exact match, not the approximate match. But anyway, so that is how the VLOOKUP works, and it's quite useful. There we go. We have our age categories. Let me save this. Now we want to create frequency tables. To do this, we're going to create a pivot table. But before we create a pivot table, go back to my data. There's something that I usually add. Now, I know there's probably easier ways. People who are more familiar with Excel will know better. I am, as a statistician, more used to working in other statistical software. But for creating counts, I have found that if I just insert an extra column, and let's just call it count, and I just put a bunch of ones in it, just ones, no other numbers, and that actually helps me in my pivot table. I'm going to take all of this data, so I will select all, and I'm going to create a pivot table under Insert, the Insert tab on the left-hand side. Insert a pivot table from the selected range and create a new worksheet and say OK. And this is what it looks like. So it comes up with absolutely nothing in the sheet itself, but it's got all the pivot fields. And now we can create anything. We can, let's have a look. Let's select our gender. Now, Excel automatically puts us under values. What I want to see is not just the sum of the gender values. That doesn't make sense. What I want to see is a frequency table, for example, of gender. So I'm going to put it in the rows, and you can see what comes up. Number 1 and number 2, and they are blanks. If I had this listed as male, female, I now know that code 1 is male and code 2 is female. We can change that in our data or afterwards in our table when we create a nice frequency table. The reason I put the count is if I drag this count into this bottom corner and it does the sum of count, it creates the frequency. So there are 115 males in this data set, 160 females, and 3 blanks. In other words, 3 missing observations. Right. So this is my frequency table of the variable gender. What if I want to create, okay, let's not do gender. So we're going to remove that from the rows. And we take our age category and drag it into the rows. And there we go. We've got our frequency table of that age category that we've just created. Something else that we can do, let's take the age category back, and we're not going to do the sum. Let's say we want to create the average age. What is the average age of the females versus the average age of males? So if I take my gender in the rows, or let's put it in the columns so you can see a different structure. So the columns, and then I take my original age into the summary value. Now it comes up with a type of summary statistic. I'm not interested in the sum. If I click on this arrow and I go to the field setting, you can see the different summary values you can get. You can get the sum, the count, the average, the minimum, maximum, standard deviation, variance. So there are quite a few things. I want to select the average, click OK, and there we go. I've got the average age for the males, the average age for females, and those three that are blank. So they didn't answer the gender, the question, but they have the age variable is there. So we can see on average, those three are a little bit older. Okay. And that's how we create our pivot table. Now, if I close this and it disappears, and I want to get it back, just right-click on your output that I've got here, and it says show the field list at the bottom. Then that comes back, and I can select anything else to create a table. At this point, if you want to make use of this information, what I would suggest is that you copy this and paste it somewhere as values. So to paste as values, I will go to the Home tab and click on Paste, the arrow, and then under Paste Values, the one that says 1, 2, 3, it will paste the actual value. So there are no formulae in it. You can see it's just the actual numbers. There are no formulae in it. So if I want to work with any of these output, I must copy it and paste it as values in a different sheet, and then I can work with it. Because if you just work with it from here and you change the table itself, you lose that information. All right. Delete this. So that wasn't actually what was asked in terms of the average. We said a frequency table of gender and note the missing value. Let's go back to a frequency table of age, because I want to, in the next question, create a bar graph of the age group. So back to this. Show me the field list again. We said we want age category. So let me just remove everything else. I want age category, and I want the counts of it. So there we have our age distribution, and what we're looking for, let me just call this the pivot table. I'm going to copy this information. I want to create a bar graph. Make a new sheet, bar graph, and paste. Oops, no, it disappeared. Sorry, back to pivot table. Copy, go to bar graph, and paste as values. So we know that this is the age category, and this is my frequency. I want to create a bar graph of these frequencies. So I highlight that. I go back to Insert, where my bar graphs right over here. Click on that selection, and that's the one I'm looking for. And there we have a bar graph of our age category, our distribution of age across the three categories. And as before, you can add labels in the vertical axis, the horizontal axis, the chart title, or if you want, you can just delete that chart title and just have whatever you want to do. So there's a lot of flexibility. If you don't like these lines, you can select them and just click delete so they disappear. Let's add the data labels. So I've got the individual counts at the top, etc., etc. So we have our bar graph of our age category distribution. And let me save my Excel file. So that wasn't too bad to create this. So anytime you create a frequency table with a pivot table, just select the information, create a new sheet, paste it as values, and then I have the input necessary for a graph such as this, or even a pie chart. Might as well do a pie chart. Let me show you the pie chart. So this is the bar graph. So insert, there's the pie chart. Let's do a pie graph. Now, why did it, where's my bar graph? Now my bar graph disappeared. Okay. Pie chart, there we go. So I have both of them. And it gives you the different categories, the slices of the pie with different colors. If you don't like the colors, you can select on each one of those separately, go to the format or even the chart design and change the chart design a little bit. If I do the pull down menu, it gives me the different options. Hover over it and I can see, is there anything here that I like, or do I want to customize it myself? And it automatically puts in this legend to say which color refers to which of the categories. It doesn't show the data labels inside, but we can ask for it. So we add the data labels, and these data labels, if you right click on them as well and you format them, let's see, we can show them as a percentage instead of the value. So it's 29%, 45%, 26%. Or you can just show the value individually, the actual counts. So there's a lot of flexibility around it. Okay, there we go. Some graphical representation. In our next question, we are going to construct, or the next two questions, we want to construct the RSE measure. But in order to do that, we have to reverse code the 5 negatively phrased rating questions. And we know that they are, let me just find my list again. Question number 3, 5, 8, 9, and 10. If I go back to Excel, to my data, I'm not going to change. So this must be question 3, 5, 8, 9, and 10. I'm not going to change this in my original data. I'm going to create new variables. And how do we reverse code? To reverse code, I've got some space to write over here. Let me just find some space here. To reverse code a 4-point scale, that is simply the formula 5 minus the scale, or minus the question. And if I've got a 5-point scale, how do I reverse code that? That is 6 minus the question. So if you go write it out, if you have codes 1, 2, 3, 4, and somebody selected 3, reverse coding means that that person should have selected a 2, because you flip the scale over. So how do I get to the value 2? It is 5 minus 3, and that's going to give me a 2. How about if somebody selected a 4? In reverse coding, that should just be a 1. So it's 5 minus 4, and that gives me a 1, and so on and so on. So that's how I reverse code a scale. And we can use the built-in functions in Excel to help us do this. I'm going to create new variables over here. That is, let's call new 3, new 5, new, what's the next one? 8, new 9, and new 10. Just want to make this a little smaller so we can fit it on one page. And we use the equal sign. So this is equals, what did we say? 5 minus question number 3. So question 5 equals 5 minus the answer for question number 5. And so on and so on. So let me quickly do this. So yeah, equals 5 minus question 8. And these 3 are next to each other. So that goes to question 9. That goes to question 10. I have my new reverse coded question. Select them all, double click on the small square at the bottom, and it fills in all of them. So I have my 5 new reverse coded questions. I can now create a sum, which is going to be my RSE variable. The sum is literally equals sum. We can use the sum function, or you can just go 1 plus the other plus, 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 or the sum, put a round bracket. And I'm now going to select all the questions that I need. But be careful that I don't include the original questions that were negatively phrased. So to do that, a very simple way to do it is effectively what you do is you are separating, you're selecting every one of the questions, the 10 questions, separating it by a comma. So I'm going to do question 1. What I'm going to do is shortcut is every time I click on something, I'm just going to click on that first one, and then I hold the control button. So it's number 1, number 2, number 3, 4, 5. I'm still holding the control button. Oops, now I shouldn't have done that 5, is it? Yeah, delete that one. So not that 5, it must be the new 5, and then number 6, number 7, new number 8, new number 9, and new number 10. So I've selected my 10 values, close the bracket, and press enter. Now, usually at this point, what you should do is just do this manually yourself for one person. Just check for one or two people whether you've actually selected the right subset, right? Or if I double click on it, it shows me question 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So it seems to be doing the right thing. Now let's just fill this in for everybody else. And there we go. We have our RSE score for the entire sample. Let me save my data. We have got that information, and what are we supposed to do with it? We've constructed it. I want to now create a box and whisker plot of the RSE measure, but do this by gender. Now, if I just did a box and whisker plot of this column, it's simple. So insert. The box and whisker plot falls under the same tab where you find the histogram. Select the box and whisker, and there we go. But that's not what I want. I don't want this box and whisker plot of just for the entire sample. I want to split this by gender. Now here Excel becomes a little finicky. You have to create something new. You have to actually create a column with the RSE measures for the one gender and another column with the RSE measures for the second gender. Now we have to create this information for some of the statistical analysis as well. So the simplest way to do it is let's add in a new sheet. And this is RSE by gender. I go to my data. I'm just going to take everything, copy it, paste it by value so that there are no formula in it. And I'm just going to delete the information that I don't want. All I want, the gender column and the RSE column. Here, I'm now going to sort my data. If I sort my data under the Home tab, where I had the filter, under that function, there's also the sort. And I select custom sort because I've got headers, I've got variable name. So my data has headers. And I'm going to sort this by gender. And then I'm just going to look for the next subset. There we go. Next code. So you can see it's a little bit manual what we have to do, and take all of this information, although those are the three genders that I'm not going to include those three. They didn't specify. So back to code 2. There we go. Unless you want to include that third category of unspecified, just move it away, cut it away, and put it over here. And now I can call this column male, this column female. I know that these are the RSE measures. And I've got my two separate columns. When I highlight this, insert, select the box and whisker plot. Now it looks different. Now I've got the one for male versus the one for female. It doesn't show the legend for this. So to show the legend, I go back to my chart design, add the chart element, and ask for a legend. And where do I want this? Let's put it at the bottom. And then it automatically puts that in. It has this column, this code 1 over here. I can just delete that. And there we go. We have our box and whisker plot comparing the two groups side by side. And obviously, when you look at this, there's hardly any difference. The behavior is very similar. We're also going to do a t-test, independent sample t-test, but we can clearly see that there's no difference between the two groups, but I'll show you how to do that anyway. All right, so that's my box and whisker plot. So there we go. Question number 9, test if males and females differ on average with respect to the RSE measure, which means we need to do that independent samples t-test. We can do this with the highlight my data, click on the data tab, go to data analysis. And first thing we want to do, let me just show you here. The t-test options are paired, 2 sample means, 2 sample assuming equal variance, 2 sample assuming unequal variance. So what's happening here, in the calculation of the test statistic for the independent sample t-test, one of the assumptions is that the variances of the 2 independent groups are equal in the population. That's a population assumption. So when I create that test statistic, and I need a standard error, I first of all pool my variances to sort of get an average, a weighted average of that. But if the variances are unequal, then it distorts it a little bit. So the test statistic has to be adjusted. So we have to test for this first to see if variances are equal or not. In that, that's another hypothesis test. The null hypothesis for testing variances says the variances are equal. Alternative, they're not. They differ from one another. We can do this in Excel. There is a test. It's called the F-test to sample for variances. So that's the first thing I'm going to do. So I select that option. My input range for variable 1. Let's make sure it selects. Let's go here. I'm going to select male for variable 1. And variable 2 is the female column. There are labels. And my output range, I'm just going to put it in this sheet itself. So my output range, I'm just going to select a cell. So the output's going to start over there. And that's all I want. I click OK. And it gives me the output for our hypothesis test. And what you're interested in is this P. It uses, let me just highlight this for you. It uses the F distribution. Now, the F distribution is a right skew distribution. There's only one rejection region, and it's under the right tail. That's why it's called one-tailed here. There's not about, is it on the left or the right of the graph? The F distribution is only a right skew distribution, so we're only doing that one-tailed. This is the p-value I am interested in. Based on this p-value, if you remember, how do we interpret p-values? This one is definitely greater than 0.1, so it's greater than 10%. Therefore, we will fail to reject the null hypothesis. We couldn't find evidence that there's a difference, so it's possibly true that the variances are equal to one another. So it seems like it is a safe assumption. So that's the first thing we're going to do. The next thing we're going to do is now to do the appropriate independent samples t-test. Back to my data tab, data analysis. Go back, now I choose this one, assuming equal variances. If this p-value was less than, say, you're testing at the 5%, typically, if it was less than 0.05, then I would assume unequal variances, and I'll have to use this formula for the independent sample t-test. But in our case, we can use the equal variance one. Click OK. Just want to make sure that I've got the right ranges. Column 1, I want column 1 over there. The first group, the second group, it's my females. I have got labels at the top. We don't have to specify the hypothesized mean difference because if the two groups are equal, the mean difference is 0, so that is built in. The output range, I don't want to overwrite my F-test, so I'm just going to put the output here in another cell or starting in that cell. Click OK, and there we go. We have our test statistic. Now, the output, it gives us a one-tailed, but typically what you're going to work with is two-tailed. So this will make more sense. It's not one of those situations where I have to be that specific. I'm just going to say for this, no, let's do a two-tailed test. I'm comparing the null hypothesis is where I'm saying the mean of males is equal to the mean of females. The alternative says the mean RSE score for males is different from the mean RSE score for females. The two-tailed hypothesis test, well, clearly that is not a significant result. So there are no differences between the groups. And we saw that visually. On average, in fact, the entire distribution seems to be very similar. So that's how I've done my independent samples t-test. Save the data. Right. Last question for this one. Go back to my questions. What are we supposed to do? Test if the RSE measure differs across the different age groups. So for this, we need to do the one-way ANOVA. As with the t-test, what I need is a similar structure. I need the RSE scores for the one age group, the second age group, and my third age group. So I need to go, again, another sheet. So this is RSE by age group. And again, a little bit work to do. Paste the values. Now I'm interested in that age category and the RSE. So that's all I want. Let me just sort my data again, so it just makes it easier. Custom sort, my data has headers, sorted by age category. Got my first age category. Let's look for the next one. Yep, there we go. And I'm going to take all the data for the next category and just move it, cut it away here, put it next to the other age category information. And my third age category, 40 plus, I'll remove this data over here. And I'm just going to label it, sorry, this is just label it with the respective age categories and delete all the excess information. We don't need that. We don't need that. Let's see what it looks like. There we go. So we've got the RSE scores for the 3 age categories. We can now do our ANOVA. Now for this one, we don't have to go and test the equality of variance. It is an assumption that the variances of the 3 independent groups are the same, but ANOVA is quite a robust test and we've got a lot of data. So that should be okay. Back to our data analysis. And we are looking for a single factor ANOVA. Click OK. My input range. So for this one, it shows not the individual variable 1, variable 2. My input range is, it automatically selected my data. I just want to make sure I've got everything, highlight all of them. And it's grouped by column. So the default is to group it by column. So it's already grouped by column. In other words, group 1 is in column 1, group 2 is in column B, and group 3 is in column C. There are labels, and my output range, I'm going to put right over here. Click OK, and there we go. We have our hypothesis test, or the results from our ANOVA, and we're interested in this p-value. It does give me the summary statistics, so the averages and variances. So there is a bit of a difference in the variance. You can look at that. But like I said, the ANOVA is a very robust test. So my p-value here is 0.086. Now, this is definitely greater than 5%, but it's less than 10%. So if I look at my interpretation, that p-value interval for interpreting the strength of the evidence in favor of the alternative hypothesis. And to remind you of the null and alternative here, what is the null hypothesis for an ANOVA? The 3 group means are equal. The alternative, at least one of the group means is different from the others. So this is a global test. All it does at this point is to say, is there a difference somewhere? Is at least one of the group means difference? Now, at the 5% level of significance, clearly there's no evidence. There's not sufficient evidence to show that at least one of the group means are different from the others. But there's moderate evidence. The p-value is between 5 and 10%. So there's moderate evidence. There's some evidence that there's a difference somewhere. The ANOVA only tests if there's a difference somewhere. What you can't do in Excel is the post hoc or multiple comparison test that will specifically show through hypothesis testing which groups are significantly different from one another. At this point, all I can do is to just look at my averages, and I can see that 2 of them are 27 point something, and the other one is 29. So it's not very strong evidence. And what you really need is that post hoc test that shows you which group is significantly different from the others, or which groups are significantly different from the others. But anyway, there we go. That is our analysis of variance, which brings me to the end of this section. So quite a lot that we've done. There we go. Quite a lot of analysis for showing the hypothesis, different hypothesis tests. Now, what I haven't shown you here is the paired sample analysis. But if I had a paired sample t-test for 2 means, what I would need is my pre-scores, that's variable 1 range, my post-scores, so maybe your blood pressure before medication for a sample of 20 people or whatever, and your blood pressure after medication, that would be your secondary variable. The hypothesized mean difference here would be 0, so we can leave that. And then we can create a paired sample t-test. And again, as before, you will look at the p-value to see what does that mean. Okay, right, so that's that. We've got one more section to look at, and then I'll open the floor for questions. One of the things that I have spoken about over the last 2 days, one of the hypothesis tests is the chi-squared tests. So if you want to compare or do hypothesis tests with categorical data, you do the chi-squared test. It's a very useful technique. What it does, it looks at what you have observed in your sample, and it looks at what you expected to observe if your null hypothesis is true. You have observed counts and expected counts, and it does a comparison between the two. So if what you observe and what you expect to observe is similar, then maybe your null hypothesis is true. Whatever that, I'll talk about the phrasing of the null and alternative hypotheses for the different tests. But if there's a big discrepancy between what you expected to observe and what you actually observe, then there's evidence that there's a difference. So a very simple example for this is, let's say I assume that the population distribution of male-female is 50-50. And I observe a sample of 20 people, and 11 are males and 9 are females. I mean, that is so close to a 50-50 split. So it's very similar to what I would have expected to observe 10 males and 10 females. So it's very similar. But in your sample of 20 people, if you observe 15 males and 5 females, but I expected, under the assumption of a 50-50 split, to observe 10 males and 10 females, that's quite a big difference. 15 males versus 10 and 5 females versus 10. So the chi-squared test will pick it up, whether you work with one variable or two variables. So the chi-squared test compares the observed counts with expected counts under the assumption of the null hypothesis. And the way we formulate the null hypothesis for the different tests are as follows. I'm going to show you two scenarios. It's the chi-squared goodness of fit test versus the chi-squared test of independence. So the chi-squared goodness of fit test is when I do inference about a single categorical variable, whereas the chi-squared test of independence is inference about a cross-tabulate two categorical variables and the association or relation between two categorical variables. So for goodness of fit tests, our null hypothesis says that all proportions are equal or that distribution follows some or other pattern. So my example of the male-female split, 50-50, that means both proportions are equal, 50-50. But if the original assumption in a particular population is that, there was in this population 70% males and 30% females, that can still be my assumption. So I've got not a 50-50 split, but a 70-30 split as a starting point. So that is the distribution follows a known pattern. So this known pattern could be the one I've just described, the 70-30 split, or that known pattern could be if I want to fit a distribution to see if data conform to a certain known distribution, such as a Poisson distribution or a binomial distribution, or even using the goodness of fit test to test whether data follow a normal distribution. All right, that's the null hypothesis. The alternative is at least one proportion is different from the others or different from the known pattern. Now, how this works is this. Why I'm giving you all these formulae, I'll try and make it as simple as possible in terms of calculation, because chi-squared tests are not built into the data analysis tool pack in Excel. Essentially, this is the test statistic, what we calculate. You're not going to need to calculate it, but you're going to must be able to calculate expected frequencies in the way I'm going to show you. But this is what it does. I'll make it a little bit bigger so you can see clearly. So for every one of my categories, so even if I've got, let's say, male, female, two categories, what I will do, I will have observed counts, which is the O, for two categories, and I will have expected counts for those two categories. So if I assume a 50-50 split, and I have a sample of 20, then my expected counts would be 10 for male and 10 for female. Whereas if I, and then I observe, let's say 11 males and 9 females, then that would be the O's, the expected counts. I calculate the difference between what I observe and what I expect to observe, and I square that difference because some of those differences could be negative. And I divide that for each one of the categories by the expected counts. Do this for all categories, add it all together, and you have your test statistic value. So how do we find the expected frequencies for a goodness of fit test? You will have frequencies in each category. To find the expected frequency for every category, you will multiply the frequency, the total sample size, sorry. So we have frequencies within each. That's my observed frequencies. The expected frequency is to take your total sample size and multiply that with your probabilities that you assume to be true to begin with. Whether it is assuming a 50-50 split, so 0.5, 0.5, or assuming a 70-30 split, so the two proportions are 0.7 and 0.3. I will just multiply each one of those respective proportions with my total sample size, and that gives me my expected frequencies. Note, in calculating expected frequencies, you don't have to round it to whole numbers. Sometimes they are decimal values, and that's okay. There's something else that we don't have to calculate this because Excel is going to do this part for us. But just so you know, the chi-squared distribution depends on a parameter, a certain parameter called the degrees of freedom. And the degrees of freedom depends on how many categories we have. So for goodness of fit tests, the degrees of freedom, if I've got two categories, male, female, it will be 2 minus 1. So the answer is 1. If I'm testing eye color and I've got 4 different eye colors, the total number of categories would be 4 minus 1, so the degrees of freedom is equal to 3. Right, so that's the chi-square goodness of fit test, and this part I'm going to show you to find the expected frequency, and then we're going to use a built-in function. Now, the chi-square test of independence works with a crosstab, so I need to be able to create a contingency table, so I'll use my pivot table to create a crosstab of counts. And for the counts, I will create a total column, a total row, and I must also calculate expected frequencies. The null and alternative hypotheses for a chi-square test of independence are as follows. Null hypothesis says they're not related. They are independent. There's no association. There's nothing happening between the two. The alternative hypothesis says they are dependent, or they are related or associated, right? So the chi-square test of independence is kind of like doing a Pearson's correlation, but with categorical data instead of with numerical data. The test statistic is exactly the same as before, where I compare the observed and expected frequencies and just calculate that for all possible combinations of my two variables, the categories of my two variables. But the expected frequencies are calculated in a different way. We need, for every possible value of each of the variables, of the first variable, let's say the row variable, we need the totals. In other words, the marginal counts. We need for the secondary variable, we need the marginal counts. So we'll have the row total multiplied by the column total for a particular combination divided by the total sample size. So think of this. If I'm comparing male, female in the rows, so I've got two categories there. And my second question is, do you drink Coca-Cola, yes or no? So I'll put that in the columns. Then I've got two categories, and that creates a 2x2 contingency table. In other words, 4 cells, 4 cross classifications with a 2x2. So I need to do this 4 times. So for the first row and the first column, I will multiply the total in the first row with the column in the total in the first column divided by the sample size. Then I go to my next one. The second row multiplied by the first column, all totals, divided by sample size. So it's very repetitive. Not rocket science, but very repetitive. In terms of degrees of freedom, it is the number of categories in the variables in the rows minus 1, multiplied by the number of categories of the variable in the column minus 1. So a 2x2 will be 2 minus 1 is 1. 2 minus 1 is 1. So it will be a 1 times 1, 1 degree of freedom. If I've got 4 categories in my rows and 5 categories in my columns, 4 minus 1 is 3. 5 minus 1 is 4. 3 times 4 is 12. So I will have 12 degrees of freedom. Right. But like I said, Excel will do that for you. So to perform these chi-square tests in Excel, we must first construct or compute those expected values using the formulae above. And then we use the built-in function in Excel to calculate the p-value of the test. So it actually makes it quite, well, relatively easy. And this is the function we're going to use, the chi-sq.test, so the chi-squared test. There's another function I'm going to show you, as if we want to calculate probabilities from, say, the Poisson distribution, something called the Poisson.dist function. We can calculate those probabilities. There are similar functions available for other distributions, such as the binomial, hypergeometric, etc., etc. All right, so let's get into it. So my third Excel sheet is, or Excel file is this. We're going to start. Sorry, I actually have questions over here. Here we go. A consumer company has 3 main cold drinks, brands A, B, and C. From historical records, brand A had a 50% market share, B a 30% market share, and C a 20% market share. The brand manager suspects that this distribution is changing. He records the units of each brand sold over the last few months, and then we have the counts, 140, 75, and 35 for the 3 respective brands. Use the chi-squared goodness of fit test to calculate, to calculate the p-value, and we interpret the results. I do want to write down the null and alternative hypotheses for you here. So the null hypothesis says the proportion for brand A, or in some cases we can use the notation pi, is equal to the original distribution of 0.5. The proportion for brand B is equal to 0.3. So if nothing has changed, this is the historical probability distribution, isn't it? The proportion for C is equal to 0.2. So that's the market share distribution from historical information. What I want to test, what is this brand manager thinking? The brand manager suspects that this distribution is changing. My null hypothesis is the neutral hypothesis that says nothing has changed. The distribution is as it has been before. So the alternative hypothesis is at least one proportion is different. Right, so let's go to our data. I've got it here in, take that away. So my expected proportions are given as the proportions in my null hypothesis. Then I've got my observed counts for each one of the 3 brands. And what I'm looking for is my expected counts. So I need to calculate this. And our expected frequencies, we said this is the sample size multiplied by the respective proportions in my null hypothesis. My sample size is 250. I'm going to multiply 250 by each one of these individual proportions. So this is just 250 multiplied by 0.5, first of all, then by 0.3 and 0.2. I just copy all that. Let me double check if it adds up to 250. Yes, it does. Put it nice in the middle. And there I have my expected counts. So that's all that's necessary, observed and expected. I can now do my chi-square using my chi-square.test function. So equals in any one of the cell, chi-square.test, put a bracket, and now it actually says the actual range. What is it looking for? It's looking for 2 things. The actual range, that's my observed information. Then you put a comma, and then you select your expected information. So the first part I select, please don't select the total. Just select for my 3 brands. That's the observed part. Put a comma. Now select the expected part. Close the bracket and enter. And there we go. There's my p-value. So it has changed. The distribution has changed because this p-value, so this is my p-value. This p-value, let's have a look at it at 3, well, 3 decimal places should do, 0.043. Well, this is definitely less than 5%, which means at the 5% level of significance, there is sufficient evidence to show me that the distribution has changed. And even if I just look at the counts, look at this. Yes, for brand B, it's still very similar. But look at that difference between the observed and expected. I expected 125. So if the original distribution was still valid, then I would have expected to observe 125 units sold. But I, in fact, observed 140. And that's at the trade-off with brand C. I expected 50 units sold, but I got 35. And this is enough for me to show that there is a significant change. Something has changed. So I will reject that null hypothesis and conclude that at the 5% level of significance, at least one proportion is different from what it was. In other words, the distribution has changed. I might as well add this in, slash the market share distribution has changed. So from a brand manager's perspective, what will I say here? Well, there's been a change in the distribution. And what's happened? More of brand A has been sold and C is going down a little bit. Okay, so that is a chi-square goodness of fit comparing this particular distribution. Now, in the same way that we've done this, we can also do this for fitting a distribution. For example, it is assumed that the number of defects in printed circuit boards occur according to a Poisson process with an average of 0.65 defects per circuit board. So my random variable x is assumed under the null hypothesis to follow a Poisson distribution with a mean or a rate lambda equals 0.65. A random sample of 60 circuit boards were tested and the number of defects observed are given in the following table. So I've got 0 defects, 1 defects, 2 or more defects. We're going to use the chi-square goodness of fit test to see if the observed distribution differs from the assumed Poisson distribution. Null and alternative hypothesis. So the null hypothesis is X follows a Poisson distribution with parameters 0. Forgot what it is already, 65. There we go, 0.65. Alternative hypothesis. I suppose I should have written this out in words. Number of defects follow a Poisson distribution with lambda equals 0.65. Alternative, number of defects do not follow this Poisson distribution. Now, in this particular example, we've got our counts. Let me go to my Excel file. What we need in this case is we've got our observed frequency counts. We need our expected proportions. Now, the expected proportions here should be according to a Poisson distribution with rate lambda 0.65. So the expected proportions, I'm going to use a built-in function, that Poisson.dist function, with a rate of lambda 0.65, and I'm going to calculate it only for the values where x is 0 or 1, but for 2 or more, I'm just going to use the complement rule to say it is everything, so 1 minus the sum of those 2 proportions I'm just going to calculate. So this equals the Poisson.dist with a bracket. The value of x would be the number of defects, so this particular value. The mean, so I put a comma, the mean is 0.65. And I don't want the cumulative distribution. I want the mass function. So if I select false, it will give me the probability mass function value for a Poisson distribution where x is equal to 0 and lambda is 0.65. So select false, close the bracket, and enter. Right. Copy this for the next one. It will automatically calculate it then for where x is equal to 1. And to find the rest of it, because I'm not going to do it for values 2 until infinity, I'm going to use the complement rule. So this equals 1 minus the sum of these two values. So I have, if I just double check, see, everything adds up to 1 as it's supposed to. I now have my expected proportions. What I'm looking for is the expected counts. The expected counts is the sample size multiplied by what I expect to occur if this distribution, in other words, under the null hypothesis, if this distribution is Poisson. So this is 60 multiplied by the expected proportion. You see, I don't have counts as in whole numbers here, but it doesn't matter. We leave it like that because I want the total to add up to 60. And now I just do my p-value again. So the p-value is the chi-square dot test function. The actual range is what I've observed over those 3 categories. The expected range are these expected counts we've just worked out. Close the bracket. And I get a p-value here that is much greater than 10%, which means, what am I going to do? I'm going to fail to reject the null hypothesis. I could not find evidence for the alternative. Therefore, the null hypothesis is possibly true. So it's reasonable assumption. So my conclusion here is to say, yes, that assumption is a reasonable assumption. The number of defects seem to follow a Poisson distribution with rate lambda 0.65. Okay, so that's the goodness of fit test. We have one more to do, and then we're done. So got a cross tabulation.
Sorry, Ms. Smith.
Oh, sorry. Yes.
Somebody in the chat box said, can we get a copy of the exercises to attempt by ourselves?
Oh, absolutely. I'm going to give you the flowchart. I'm going to give you these data files with all the exercises I've done, and I'm going to give you this document in PDF format. So absolutely, all of this you're going to get.
Okay, perfect. So just for the participants to know where the videos will be posted on RCDMS. So if you joined through RCDMS after the event, you can always go and download or listen to the workshop recording, because we will upload it on RCDMS and we will also upload it on our model communities. On our model communities under our workshop resources for 2025, you will see it for these workshops. So
yes,
everything will upload it. Yes.
Thank you for that, Lawrence, because, something like this that is so, analytical, when I do actually examples, it's very difficult to put together a PowerPoint presentation for this. So it's more hands-on, and I'm glad the video will be available. I know it's a long one, but then students can go, or the participants can go through that and just see what I've done. But I will provide everything that I've done today, all those documents, Excel and PDF files I will provide. Okay.
Oh, okay, perfect. And we'll definitely share with all the participants. Thank you.
Awesome. Okay. All right. Then the last one here, we've got a cross tabulation. So this cross tab is, if I had the raw data, then I can just do a pivot table and create this cross tab, and it will give me this part. It'll only give me this part. Not in the table, it will show totals, but you will take this part and create a new sheet, copy the data and paste it as values, and then create your own totals just using sums. So what we have here, these are the row totals, these are the column totals, and this is the sample size n. So I can write this. This is my row totals. These are my column totals. Even if I swap the variables and I have male, female in the rows and the rating scale answers in the columns, it doesn't change things. At the end of the day, it doesn't matter if you swap the rows and columns around, it's going to give us exact same information. So for this particular one, well, null and alternative hypothesis for chi-square test of independence. So the null hypothesis says that gender and rating are independent, or you can write not associated, not related, means the same thing, versus the alternative, very simply, gender and rating are dependent. Now, what we want to do here is to calculate the expected frequencies. Now, the expected frequencies is calculated for every one of these. There are 6 cells in this cross tab. So it's a 3 by 2 matrix. So I've got 6 intersections here. So for each one of those 6, I have to do the following. I'm going to do this stepwise so you see. So this is the observed counts for males who agree. I want to calculate what would I expect to observe if gender and agreement or rating scale are independent. So this goes back to statistical independence, where we said the probability of an intersection of events, if they're independent, is just the probability of the product of the marginal distributions. And we're going to just convert these probabilities to counts rather than distributions, but effectively that's what we're doing. So the expected intersection count, if they were independent, would simply be a function of the 2 marginal counts, right? How do we do this? I'm going to take the row total, multiply that with a column total, and divide by sample size, and I'll get my expected count. If I do this for the next one, I will follow the same pattern. This is a very repetitive pattern. So for this one, observe 35. What do I expect to observe? Row total times column total divided by sample size. Let's do one more. Let's pick, okay, we'll pick this one. So observe 23. What is the expected frequency under the assumption of independence? Row total times column total divided by sample size. And that's what we do for all 6 of them. And we're going to do that in Excel now. Right, back to Excel, my independence. So this is my observed. I'm just going to copy this and call this my expected. No data in here yet. So what I'm going to do is I'm going to put a formula in, and me being lazy to type everything, I'm going to try and make the formula so that when I copy it over all 6 cells, that it does everything. Okay. So that's what we need. So what we need to do for every one of these cells is to take the row total times the column total divided by the sample size. Is that right? 162. Yes. And I showed you once before when I did the VLOOKUP that we can fix cells by putting dollar notation. But the dollar notation, if it goes in front of the column numbering, then it fixes the column. If it goes in front of the row numbering, it fixes the row. So in certain cases, I'm going to fix the column. In certain cases, I'm going to fix the row. Or you can just do this formula 6 times if you want. Here we go. It is equal to, I need to put I don't have to put a bracket. So I want the row total. So in this particular case, I want to fix the row, the column. I want to fix D. So I want to put $1 in front of D2, or using your F4 function. If I do it once, it puts dollars both before the D and the 2. Do it again. It only puts it in front of the row. Do it a third time, it puts it in front of the column. So I want to fix that column D. And you'll see now what I mean by that. So if I go for the next level or for the next row along, I don't want to read the answer from column E. I want to always read it from column D. This I'm going to multiply with this row 5. All the row information is in row 5. So I need to fix row 5. So back to my function F4. Once fixes both of them. Second one, oh yes, the dollar is in front of the row. I want to fix the row and here, keep it constant. This I divide by my sample size. And now I want to fix the row and the column. So that's just the F4 twice. So it shows you how the dollar notation is kept. So that's my expected frequency for the first cell. Now see what happened when I just copy and paste this to all the cells. You will see, I will select one. Look at that. Because I fixed it appropriately, it selects the correct row, which is row number 3 in Excel. Selects the correct column, which is column D, and it still uses my sample size. Let's look at another one. How about this one? This is in my 3rd row, so it is in, oops, no, this didn't work. Yes, it is, it did. So it is still in row 5, still in column D, to get me that expected frequency. So now we can do our chi-square. My p-value equals chi-square dot test. My actual range, I literally just highlight all 6 of them in a block, comma, and do the corresponding 6 over here with expected, close the bracket, equals, and there we go. We have our p-value. And this is highly significant. This is less than 1%. So this is a highly significant result. If I quickly go back to my null and alternative hypotheses, I've got such a small p-value. It falls in that interval between 0 and 1%. That gives me very strong evidence for the alternative hypothesis. So I have found very strong evidence to support that gender and rating are dependent on one another. If I look, I just want to make fewer decimals, too many decimals, it's very crazy. So if gender and agreement rating scale were independent of one another, these would have been the counts, make it to 1 decimal, 0 decimals, would have been the counts that I would have observed approximately out of a sample of 162. But in reality, what did I observe? I expected 45 males who agree, but I got 58. That's quite a big difference, isn't it? I expected 23 females who disagree, 25 females who are neutral. I got 18. So all over the show, there's quite a difference in what I have between with what I've observed and expected to observe. So we can then look at a comparison, like I've just done, sort of on its own. There are some techniques to now go and show you what are the key differences, the strongest differences. But this is enough to say there's definitely some sort of an association between whether you're male or female and your level of agreement on the scale, whatever the scale measured. All right.
Okay.
And that's how we, yes.
Just to interject, somebody in the chat box said, not sure if I saw correctly, please revisit the pivot, I think, for the expected data on disagree KTA referencing the total.
Sorry, and calculating the expected frequency for test of independence.
Yes, referencing the total, yeah.
Okay. Oh, you mean in terms of calculating it?
Yes, I think so. Yeah, I think that's
okay.
part, yeah.
All right. So let me go back to the formula. There is a formula. No problem. So I need for every one of my, okay, let me show you the notation. So EIJ would be the expected frequency in a row I, column J. So go back to our data. We have got 3 categories in the row.
Sorry, Ms. Smith.
Yes.
You said not the pivot, sorry, the VLOOKUP. The participant said the VLOOKUP.
Oh.
You can also unmute your mic and speak just to clarify your question.
Okay.
There, one delay if you want.
So, okay, can I just put, before we go into that, so this, I'll speak to the VLOOKUP in a minute. Okay. So I just want to, let me finish this off. Finish this off, then I know I'm done and we can answer any questions. So this is the chi-square. So the chi-square test, it's not built in, but there are some things built in that can help us do this. So I'm hoping that this will help you a little bit. And at this point, that comes to the end of all my analysis that I wanted to show you. And I'm happy to now address any questions you have. One of the questions was specifically on the VLOOKUP, how that works. So maybe the participant can just put the mic on and just ask your question. Thank you.
Good day, ma'am. How are you?
Hello.
I'm not sure if the VLOOKUP formula you just did was referencing the correct cell within the disagree parts for females. I think it was referencing the total.
Oh, you mean in the
okay,
so it's not VLOOKUP. Sorry. So go back to this. Did I do a mistake? Are you still talking about the chi-squared that I did?
Yes.
Okay, so the VLOOKUP is not in here. It's just the.
Oh, I thought you used the VLOOKUP formula.
No. What I meant when I said that is, remember with the VLOOKUP, I'll go back to the VLOOKUP. Where did we do VLOOKUP? It was in the RSE data, the VLOOKUP. If you look at the function for the VLOOKUP, it referenced the H category, those 6 cells. So this block of cells. So it's from row 2 to 4, column A to column B, and I wanted to keep that fixed. So what I did with this was to put $1 in front of the row A and row B, goes to A to B, and dollar in front of row 2 to row 4. And what I meant with in terms of the chi-squared, if you look at this part here, that $5, $D, $5 keeps this cell, this one here, the 162 fixed. So even if I copy this function anywhere, it's going to give me something funny. It still refers to D5, but it now uses another column in another row. Are you with me on that? So the function for the expected value, or the calculation for the expected value, a value, so male, agree, that sits in row 1, column 1, or in this case, row 2 in Excel, so row label 2, but that's my first row of the table in terms of the values of the variables, and in column B. So I need to use the row total, which sits in column D, and the column total, which sits in row 5. But if I move over to female, I'm still looking at all my row totals sit in column D. So whenever I refer to a row total here, I want to keep row D fixed. And when I do the column totals, they all sit in row 5. So they're over different columns, but they all sit in row 5. And that is why the function itself, the first part, reference the row total. So it will be over row 2, 3, and 4, but all three of those numbers sit in column D. The second part is my column totals. So that is over column B and C, but both of them sit in row 5. So I want to keep row 5 fixed. And that's why the dollar is in front of the row for the column totals. And here the dollar is in front of the column for the row totals. And then I divide by the sample size, which for all 6 intersections must come from column D, row 5. So I just fix it that way. If you don't want to do it this way, we can do the following. You can do it bit by bit. So let me just take this out. You don't have to use the dollar notification. You can just do the function 6 times. Equals this row total multiplied by column total divided by sample size, and enter. The next one equals row total multiplied by column total divided by sample size. I think you see what I'm doing here. I'm just doing each individually. Row times column divided by sample. And then I just do it for the next one as well. Equals row times column divided by sample. Might be good to do it for the first run, just so that you get comfortable of how to do this. And it gives the same answers. I'm going to stop at this point now. Or I might as well finish. Equals row times column over sample size equals row times, just make sure you always pick the right one, and we end up with the exact same values. The dollar the dollar notation in Excel just helps us that if I do something repetitive, like you've just seen, that if I know how to keep something fixed, then it just saves some time. I could just do it once and just apply that to a number of different cells, and it should pick it up. So I hope that answers your question and helps. Okay.
Yes, thank you very much.
You're very welcome. I think I'm going to leave this here so you can see if we just do this individually when you get the documents. All right. Any other questions?
Just someone asking, can we have your email for consultation, please?
Okay. Well, yeah, I'm not sure I can get involved too much in consultation. I'm happy to guide maybe a little bit, but I think that, your supervisors probably have done quite a lot of work already from a statistical perspective. And maybe, are you guys making use of StatCon, or are you just doing all this by yourself?
Yeah, most of them should be aware. She said for guidance. I see you have your hand up there. Do you want to unmute and speak? Another?
Good day, everybody. I'm new with the stats part because when I was doing my BTEC, I just used the graphs. So now it's like I'm learning new things with Excel. I just want to find out for me when I have to calculate the p-value, do I have to start with the chi-square part?
Well, it depends on which test you are doing. So every hypothesis test, every single hypothesis test that you will ever come across will produce a p-value. For example, when I did the independent samples t-test, just the f-test, the equality of variance test, that's the p-value. The outcome here, that's the p-value. So every hypothesis test yields a p-value. You don't have to go and calculate it. That's the beauty of statistical software. But understanding what it is, perhaps, I don't know if you were in yesterday's session, but if not, Lawrence, you can maybe answer this question. If all those sessions that I did yesterday and the day before, specifically yesterday with inference, if that is available for all the students to talk a little bit about what is a p-value. You don't have to go and calculate it yourself. If you use Excel or SPSS or whatever, it will calculate it automatically for any hypothesis test you're doing. The reason why I showed you how we do the chi-squared one, there's a little bit more involved, is because the chi-squared test is not built in as part of the data analysis itself. Unfortunately, it's not listed here. But thankfully, the chi-square p-value calculation, that function, you can actually just use the chi-square.test function by specifying the observed and specifying the expected, and it will return the p-value. So it will calculate it for you. Because calculating p-values, I mean, it's by hand. No, you let the computer do that for you. What is important, though, is that you know how to interpret that. And that's in the session I did yesterday, but I think the recording and the PowerPoint presentation is available. The PDF file, rather, yeah, PowerPoint is available for that.
Okay, so I'll also show them in the end how to access this recording or the material as well, both on our CPMS and both on our model communities. Right at the end, I'll just show them how they can be able to access that, because I feel some of the participants are struggling to access the recording. So I'll just show them at the end of the session. All right, thank you.
All right, thanks. So the participant who just asked me about how to calculate the p-values, I think just know that you're not going to calculate it. The program, and depending on your hypothesis test, it will give you a p-value, but you need to know how to interpret that. And in order to interpret that, you must actually have a good understanding of what is my null and my alternative hypothesis for the particular test that I can do. So if you can get access to yesterday's presentation, maybe that will help a little bit. Okay, any other questions?
I can speak.
Yes, I have just a small question.
Sure.
I just wanted to find out the data analysis module you're using on Excel. Is it like a plugin, or can you find it under?
So it's under, if you click on File, go to Options, and go to Add-ins, you're looking for the Analysis Tool Pack. And if you're not sure, there's another thing. Google is my friend. So here we go. How to add Excel data analysis in Excel. The first thing, go to Enable the Data Analysis Tool Pack, and it will tell you how to enable it. Open it, navigate to Options, access the add-ins, and click Go. So that helps. That's just an add-in that you need to select. And then it comes up and shows under your Data tab.
Thank you.
You're welcome. Anybody else?
Any other questions from the participants? You can also type in the chat box, or you can raise your hand so that you can just get clarification on what you might not have understood properly there. I don't know if you're going to be sharing your email there, Mr. Lazard.
Well, you know what? Look, I love, let me just, I think I can stop sharing now. Hold on, let me just find it now. How do I stop? Come on. Stop sharing. Stop sharing. There we go. I'm going to stop sharing now. So the I don't. If the problem is, if I think if I just give my email address and start getting involved in quite a lot of this, that might just become a bit difficult and overwhelming. So I think starting point, perhaps look at first of all the sessions that we have done, and Lawrence, maybe you can also just echo this or just comment on it. There is still StatCon, so the Statistical Consultation Service. I don't know if they
Yes,
work for
certainly,
honors
yeah.
students or if it's just for masters and PhD. Do you know or how they deal with it
They work for
nowadays?
all postgraduate, as long from honors upwards.
Is it from honors? So,
Yes, it's
but
from
they are
honors.
there to give advice. At the end of the day, even if you want to do your analysis yourself, but you still want to get some advice from them, just contact them, get in touch and ask and see to what extent they can help. At the end of the day, I know that StatCon, I worked there many, many, many years ago, and we used to do the analysis for students, right? And then do the interpretation, show them what it means, and then students would go and write it up. I don't know how that has changed, how much that has changed, and about their availability and flexibility and what they're doing nowadays. But I think the best would be if you need some assistance, they're there. Go and ask. You and your supervisor, get in touch with them and find out. They are just outside of APK campus and find out to what extent they can help. But hopefully, the information that I've provided to you now will give you a little bit more of an understanding of when you do research, that I propose the right techniques, and maybe just understanding p-values a little better, just understanding that what the tests are, what are involved in all of these analyses. So that will help you to design it better, to address your questions, and then when it comes to interpretation, to be able to just use your insight and have insight and understanding of what it really means. So definitely StatCon is there. I wish I could tell all of you, yes, sure, come and have a chat with me, because it's always very interesting. But I don't I think my HOD is going to be very happy if I get too involved in something like this, as I am still teaching at the statistics department and I'm not officially involved in consultation like this. So sorry, I don't think I'll be able to help you to that extent.
Natural. So StatCon is always going to be is always available for postgraduate students from honors level all the way up to PhD. The office is situated outside APK campus, outside Gate 2, I think, by the roundabout. So
Yes.
you can always, take a walk there and try and ask how they can assist you, or how you can also book an appointment with them, and they're always available to assist all the postgraduate students. Yeah.
You can just Google, or I don't know if it's on the website. If not, just Google and find out if you can just get an email. I think there is an email address for StatCon itself, and maybe just send them an email if you need some assistance.
Yes, perfect. So can I just show the students how they can be able to access the recording? So with the students that have joined through RCDMS, can you just please allow me to share my screen? Okay, so I don't know, I hope everybody can see my screen there. So if you have joined through RCDMS, so you go into the RCDMS, then from there you navigate to the corner there on the left-hand side panel. So then after doing that, you go onto the calendar, because this is from my admin side, so it will be different from the student side. So when you go there, you will see where it says my events, then you click on my events, then you go onto the calendar. And you go onto the calendar there. Then once you get to the calendar, you should be able to see all the June workshops that have been going on. So from there, you'll be able to navigate. So we are going to upload all the videos on RCDMS as well as on Moodle. So as you can see there on Tuesday, we had statistical analysis, probability and distribution. So you click on it, then you click on view event. Then you go on watch recording where it says event recording right there. So once you click on it, it will take you to our YouTube page. As you can see there, the recording hasn't been uploaded yet. So when you click there, you'll see the recording will pop up right there and there. As you can see, let me just give you another example with the introduction to Atlas TI. If you view event and click on watch recording, then certainly it will take you straight to our YouTube page right there. Then you can be able to watch the recording from there. I hope everybody is fine there. If you have any questions, please let me know. Then from the model community side, let me just also share my screen. But if you do have any questions, please let me know, then I can guide you through as well. Then from the model community side, you can always go on ULink. Yes, once you get on ULink, if you registered on our model communities, whether it's the coursework community, the supervisor, the postdoc, or the research masters. So let's say, for example, you are registered into the research masters and doctoral. So you click on it, then it will take you in. From there, you scroll down to 2025 monthly workshop and resources. Then you click on it right there. Then you navigate to June, as now we are in June. And from there, you click in June. You click there on June. Sorry about that. You click in June. Okay, then once there, you'll navigate. Then you'll see all the workshop recordings will be posted. Some of them, they are yet to be posted. So from there, you'll see where it says recording link. As you can see there, these ones have been recorded already. The one for the 9th is there, 17th is there, and the one from yesterday is recorded, is uploaded as well. Then you will record all of them, as you can see there, with the workshop resources from this side. So everything is hyperlinked. The presentation slides are also hyperlinked. So from there, you'll be clicking on the hyperlink which says click here, then you'll be able to download all the workshop recordings from there. If you're not registered on any of our model communities, please kindly send an email to RCD inquiries. Then I will be able to register you on our model communities from there. Okay, so from there, I'll just stop sharing my screen. Okay, I'll just type in the email in the chat box. So RCD inquiries at uj.ac.za. But I'm sure most of you are also registered on RCDMS. So if it's easier to get everything on RCDMS because you just click watch recording, then it will take you straight to the YouTube page. Then you'll be able to attend from there. Sorry, to watch the recording from there. But if you do have any further questions, please feel free to email rcdinquiries@uj.ac.za and we'll be able to assist going forward. I don't know if there's any further questions from anyone here, from the participants, to Ms. Smith before we can end the session, or from me regarding the recording or anything regarding that from the participants, or we're all good. Maybe you can just indicate with a thumbs up if we are all sorted. All right, thank you so much. So in that regard, once again, thank you so much, Ms. Smith, for presenting on this series of workshop, rather. So we're calling it a series of workshops. Since Tuesday, you did the probability and distribution, the inferential statistics on Wednesday, and today you did the statistical analysis using Microsoft Excel, statistical and visualization. And we really, really do appreciate your support to the Research Capacity Development Unit, and hopefully we will be having future collaborations going forward. So in that regard, thank you so much. Thank you so much. We really, really do appreciate your support to
It
the
is
Research
the greatest of pleasures. It really is a great pleasure, Lawrence. And I just want to say to all the students, I wish you all the very best. I hope that this has been helpful. I know it's quite overwhelming because I showed you quite a lot of things, but play around with it. You need to understand your data and understand how you can use your data to answer your questions. So I wish you all the very best of luck with your research. And I'm looking forward to our future collaboration, Lawrence. Thank you so
No,
much,
certainly.
everybody.
Certainly. So in that regard, I will now be ending the session. I've also posted the feedback survey. Please kindly fill that in. And also this will allow you to get a certificate of attendance for this workshop. And going forward, thank you so much to all the participants for joining. And thank you so much again to you, Ms. Smith. And thank you so much again. Hopefully we will collaborate in the future going forward. And in that regard, I'll now be ending this session. Thank you so much to you again, Ms. Smith. And thank you so much to the participants, and enjoy the rest of your day further. Thank you so much.
Thank you, everybody. Take
So
care.
much. Thank you so
Bye-bye.
much.
All right. Thank you, guys. Bye.
Bye.
Thank you.